Here are solutions to homework set number 6 for ECE 111. This homework looks at solving problems that you'll encounter when you take Math 165 differentiation using Matlab. With Matlab, you can use numerical techniques to solve many problems that you'll encounter in those courses. The first problem is just looking at what is a derivative. A derivative is slope. So if I have a function like the following, the slope would be the derivative. Derivative, like dy dt, is the change in y with respect to t. So between 0 and 1 second, y changes by 0 in 1 second, so the slope is 0. Between 1 and 3, it changes by 1 in 2 seconds, so the slope is 1/2. So it jumps up to 1/2 and comes over. Between 3 and 4, y changes by 4 in 1 second, so the derivative jumps up to 4. Again, the slope becomes 0. Change the y of 0 in 1 second, and then goes down, negative. 1, 2, 3, 4, 5. Drops 5 in 1 second, comes down to -5. Now it drops down 2 in 2 seconds, which is -1. Plus 3 in 1 second, plus 3, then back down to 0. So there's the derivative. Again, derivative is just slope. So if you have a curve, you can find the derivative by hand, just by measuring the slope at any given point. I can do numerical differentiation. Numerical differentiation is the same idea. Given a point, like here's a curve, I want to find the derivative at this point. Here's y, x. Take y of I plus 1 minus y of I minus 1. This distance is dy. This distance is dx. The ratio is the slope. That's roughly the slope at this point. So problem 2 says, let's use numerical differentiation to find the derivative of a function. So here's a function, sine of x over x, plus 0.001. When you take calculus, you'll be able to find this by hand. Now, using Matlab, even if you don't know calculus, you can still find the derivative using numerical techniques. The first trick is to come up with a function. I pass x and y, and it finds the derivative at any given point using this algorithm. The oddities are the endpoints. I can't go beyond the endpoint, so it's slightly different at the endpoints. Given that function, I can now say, take this function, find its derivative. So given x, calculate y. Now call your function derivative. Given x and y, find the derivative, dy. If I plot it, the blue curve is y. The red curve is the derivative. I'm going to call y prime. Another way to symbolize derivative is y prime or y dot. You kind of notice when the slope is 0, the derivative is 0. When the slope is increasing, derivative is maximum. When the slope is decreasing at the max rate, it's negative maximum. One use of derivatives, something you'll be doing when you take differentiation, I can use the derivative to find the maximum and the minimums. So when the derivative is 0, like right here, that's a maximum. Here's another point where the derivative is 0. That's minimum. Given a different function, like here's another function. Given the function, input it into Matlab, find the derivative. So here's y in blue. Here's y prime in red. So that's the beauty of numerical differentiation. Even if you don't know how to find the derivative, if I get the function into Matlab, Matlab can find the derivative. Problem 4 looks at path planning. Suppose I have this function. I'm going to go from 0 to 1 radian following this path. For t less than 0, it's 0. Then an increase as t over 3, then it's 1. Calculate the velocity and acceleration of a robot that follows that path. Well, the derivative, first input the function into Matlab. Take the derivative, that'll be the velocity. Take the derivative again, that's acceleration. If I plot it, here's your function, this is y. Here's the derivative, that's the velocity. And the green line is the second derivative, acceleration. Now this is actually kind of a bad path. This is a motor. The voltage, roughly, is the velocity. The current, roughly, is the acceleration. I need the current to go to infinity to start the motor infinity, minus infinity to stop it. Infinite current's kind of a problem, burns out motors. So this is probably a bad path. But if I assume a different path, here's a cosine interpolation. I'm going to start out at 0, increases the cosine function, and then stop at 1. So if the cosine was continuing, here's what the cosine would look like. I'm just going to pull off this part of the cosine and go from 0 to 1. If I did that for path planning, find the velocity and acceleration. Again, same trick. I'll throw the function into Matlab, find the first derivative, find the second derivative, and here's what she looks like. So this is the position. The red line is velocity. That'd be the voltage to the motor. The green line is acceleration. That's the current to the motor. This is a much better, more reasonable path for a robot arm or a motor. To go from 0 to 1 radian, if I follow this path, I have finite voltages and finite current. And you kind of do that when you take robotics. It's how to go from point A to point B. All paths are not equal. Some of them are more reasonable, meaning I have finite current. Some you just can't do. For example, the first one, where the current is infinity. Problem 6. Assume the motor's angle follows this function. So this is a little bit different. I'm going to go from 0 to 1. For the first 1.5 seconds, I follow a parabola. The second 1.5 seconds, I follow another parabola. Then I stop at 1. If that was my path, find the velocity, acceleration, meaning find the voltage and current. Throw that into Matlab, in kind of a long function here. Kind of what this does, here's your function, valid for t bigger than 1.5 and less than 3. Here's the function, valid for t bigger than 3, and a function valid for t less than 1.5. If I do that, here is your function y. The red line is y prime. The green line is y double prime. So this is just another way to go from 0 to 1. The advantage of this approach is the acceleration is a constant. Velocity, it speeds up, then slows down. Another path. So that is homework set number 6 for ECE 111. With derivatives, you find the slope of a function, and one application of derivatives, well, one application is to find the maximum and minimum of a function. The maximum and minimum occurs when the derivative is 0. The last part is, given a path going from A to B, I can find the implied voltage to a motor and the current to the motor. Homework set 6 for ECE 111. I should also mention, this is the beauty of Matlab. Even if I don't know how to do derivatives, if I can get the function into Matlab, I can calculate the derivative. When you take Math 165 differentiation, you'll be able to calculate those derivatives by hand. But even if you haven't had that, Matlab can still find the answer.